Prim's algorithm is an example of a general graph traversal algorithm that we have talked about earlier in the pre-class videos on graphs. So the algorithm starts out with some source vertex, and this could be any vertex that we choose, and all the edges that are coming out of that source vertex are going into the other partition initially, and the neighbors on the other side are known to exist. So they are sort of discovered as soon as we look across the adjacency list of the source. But there could be other vertices whose existence is not yet known to us. So generally speaking, every vertex goes through three phases in its life cycle. It starts out being undiscovered, and that's what I have here, when we don't know whether that vertex even exists. At some point we see a fringe edge or a cut edge going across to that vertex, and that is the point where it is discovered. And when it is discovered, it is typically added to some kind of data structure. For example, in breadth first search, as soon as we discover a vertex, as soon as we visit a vertex, we immediately add it to the queue. So the vertices that reside here are essentially part of a data structure. It could be a queue, it could be a stack, it could be some other kind of data structure, as we'll see. But at some point their turn comes to be popped out of that data structure and to be dragged to the left into this captured set on the left hand side, and that is the point when that vertex is attains its final position in this captured array, and that's when we sort of look at all its neighbors in its adjacency list, and if we find some neighbors that have not yet been discovered, we mark them as discovered and we add them to that data structure. We could also see some neighbors there that are already discovered, but we might see fresh edges going across to those neighbors. And we also might find some other neighbors which are already part of the captured set. So we have to simulate this whole process, and the question is, how do we do that? So in Prim's algorithm, what we want is that if our edge weights, for example, are 1, 2, 3, 4, 5 and 6 here, we want to decide which vertex is to be dragged from the right hand side to the left hand side. And conceptually we want to pick that edge whose weight is minimum. So you can see that this is the edge with the minimum weight, and so we want to pull on that edge and drag the vertex on the other side into the captured set. So what kind of data structure would allow us to provide ready access to the vertex for which we have that lowest cost edge on the cut? So we want the vertex with the lowest cost cut edge, to be most readily available, and that is the vertex that we will extract out from that data structure and drag it to the left. So if each vertex is associated with some kind of priority value, and that priority value happens to be the weight of the lowest cost cut edge that is reaching it from the left hand side, then a priority queue might give us ready access to that vertex. So the data structure that we are thinking of here is basically a priority queue to store all these discovered vertices, and the priority value associated with each vertex is going to be the weight of the lowest cost cut edge that is reaching it. So for example, if we look at this vertex, there are two edges across the cut that are reaching it. The first edge has a cost of 6, the second edge has a cost of 4, which is reaching it, and so the priority value that we want associated with this vertex would be a 4. If you look at this vertex, there is a single edge that is reaching it, which has a weight 5, and so we want the priority value associated with this vertex to be 5. This vertex has two edges coming into it across the cut. Between them, the lower cost edge is of weight 2, and so we have the priority value for this vertex being 2, and likewise the priority value for this vertex is the weight of this single edge reaching it, which is 1. So assuming that lower values for the priority signify higher importance, we want the vertex with the lowest priority to be available at the head of the priority queue, so that when we ask for the lowest cost edge to be included in the spanning tree, effectively we are going to drag the vertex with the lowest priority across from the right hand side to the left hand side. And when we do that, when we drag the vertex from the right hand side to the left hand side, let's say we do that for this particular vertex, so this vertex is going to reach the left hand side, and the edge to it basically becomes a part of the spanning tree. And now we look at the adjacency list of that vertex. Maybe the adjacency list of that vertex had a neighbor which was so far undiscovered. If so, we are going to take that neighbor and add it to the priority queue. It's going to move from the undiscovered set into the discovered set, and its priority value in the priority queue is going to be the cost of the edge that is going across from this edge on the left hand side to it. So if the cost, for example, was 7, then this vertex is going to be associated with a priority of 7 when it moves into the priority queue. So I shouldn't be showing it here. I should remove it from there and put it in the priority queue here with priority value 7. It's also possible that the vertex that we had just dragged across had a neighbor which already lies in the captured set, in which case the weight of this edge, whatever that weight W is, doesn't matter, because that edge has no importance, since both these vertices are already part of this growing spanning tree. So we don't care about these additional edges, which will only create cycles if we were to add them to the growing structure. It is also possible that this vertex has an edge going to an existing vertex in the priority queue. So maybe this vertex over here. Now the priority value associated with this vertex is a 2, but what if the edge weight going across from this vertex to that vertex is a 1? If the priority value is 1, we basically need to update the priority of this vertex to now become 1 instead of 2, because the lowest cost cut edge now reaching it has a weight of 1. So within the priority queue, there has to be a way to change the priority of a vertex. It's like a bunch of patients waiting in the emergency room according to the severity of their symptoms. That's their priority value, and at some point we may find that one of the patients suddenly has his or her symptoms worsen, in which case the priority value has to be changed. The patient has to be moved further ahead to the head of the towards the head of the queue. So that's the analog of what we are doing to these vertices. Every time we see a cut edge going to a vertex which already exists in the priority queue, but that cut edge has a lower cost weight than the priority value of that vertex, we have to decrease the priority value to be equal to the weight of that cut edge. Now unfortunately, standard priority queue libraries in the languages which provide them don't include this operation for decreasing the priority of a vertex. So that is a severe limitation, because if we have to use that decrease key operation, we have to implement a heap ourselves, and that is not going to be practical in an interview setting where we have a severe time limitation. So I'm going to show you how to bypass that constraint in a bit. First, we'll just assume that we have an operation for decreasing the priority of a vertex in a priority queue, and understand how that algorithm works, and then we'll see how to bypass the limitations from not having the decrease queue operation available to us. So let's write the pseudocode for Prim's algorithm following the procedure that we have discussed. So our algorithm is going to pick an arbitrary vertex in the graph to start our general graph traversal from. Let's say the vertex we start from is the one with ID 0. We're going to treat it like the source vertex, and so this is the lone vertex that's going to start out here on the left hand side. So we have to mark it as being present on the left hand side. So what tag should we use for it? Well, we are going to use the captured tag. So let's initialize a captured array, which is going to be a one-dimensional array of size n, initialized to -1, similar to what we did in the graphs class with the visited array, and we will set the captured value for that source vertex, let's say it's the vertex with ID 0, to be 1, indicating that this vertex lies on the left hand side. All other vertices have a captured value of -1, indicating that they lie on the right hand side. We also have a priority queue, right? Let's say it's the variable pq, which is going to be an empty priority queue, and it starts out empty, but it's going to get filled quickly with a bunch of vertices. So what we will do is we will look out from the source vertex. So if this is the vertex with ID 0, we're going to look at all the outgoing neighbors of that vertex 0, and we're going to add those neighbors to the priority queue with a priority value equal to the weight of the edges going to them. Now, since this graph is a weighted graph, there are going to be some differences between how we build the graph when the edges are given to have weights. So let me pause the code here for a moment, and let's go back to step 1, which is really the first step in our code to build the graph. So let's see how we are first going to build the graph, and this is going to look similar to what it looked like for BFS and DFS, with some small differences. So we are going to initialize an adjacency list as a one-dimensional array of size n, pointing initially to empty lists of integers. So it's going to look like this. It's basically an array of size n, and each of these indices points to an empty adjacency list, right? So the adjacency list of I is basically a pointer to a list of neighbors of vertex I in the graph, but of course we haven't yet populated these lists of neighbors. We'll assume that n is the number of vertices as before, and we'll assume that our edges are given in an array called connections. So connections is going to be an array or a list of triplets of the form u, v, cost. Right, so these are undirected edges, and when we see an edge u, v, cost, what do we do? So for each edge that we see of the form u, v, cost in this array or list called connections, we are going to add it 2 times to the adjacency list structure here. We will go to the adjacency list of u and add v to it, but this time, because the graph is weighted, we are not just going to add v, we will also add the weight of the edge between u and v along with that neighbor v. So stored along with that neighbor is the cost of the edge to that neighbor. And this is an undirected graph, so we have to do the converse as well. We have to go to the adjacency list of v and add to it the neighbor u associated with that same cost. And so this would populate the adjacency list structure here, and following this we move to the code that we wrote a few minutes ago, which I have pulled down here. So we have a captured array that is also initialized to -1s except for the source vertex. We also have a priority queue which is initialized to an empty heap, an empty min heap, you can say. But for each outgoing neighbor of the source vertex, for each outgoing neighbor, and remember that neighbor is also associated with a cost, for each neighbor comma cost in the adjacency list of that source, right, the source has ID 0, what we will do is we will add that neighbor to the priority queue. So we're going to insert into the priority queue the neighbor with the priority value being equal to the cost of that edge. So what we have at this point is basically this captured set on the left with just the vertex with ID 0 in it, and if it had, let's say, 3 neighbors, we have all the other vertices on the right hand side. Most of them lie undiscovered over here, but 3 of those vertices, which are the neighbors of 0, lie in the priority queue, and their priority values are basically the costs of these 3 edges. Now in each step, now we are going to pull one vertex out of the priority queue, drag it to the left, look at its outgoing neighbors, see if any of them is undiscovered. If so, we will insert those neighbors into the priority queue. So let's write the code for that. We are going to keep doing that as long as the priority queue is non-empty. This is similar to what we were doing in BFS. So while there's going to be a while loop which will say while the priority queue is not empty, we will pop the next node from the priority queue. So basically the node with its priority value is going to be popped out of the priority queue, right? So this is basically an extract min operation. And then if we were maintaining the total cost of the spanning tree, so let's say we do that here, let's say we have a total cost which is initialized to 0. What we will do is, since we are dragging this node to the left, we are inserting one extra edge into the spanning tree, and that happened to be the edge with the lowest weight across the cut, which is also the priority value of the vertex in the min heap which we are dragging across now. So the total cost is going to go up by that priority value, and apart from that we are going to mark the fact that this node is being captured. It's moving to the left, so captured of node will be 1, and then we are going to look at its outgoing neighbors, right? So for each neighbor in the adjacency list of that newly captured node, and each neighbor is associated with a cost of the weight of the edge going to that neighbor, we are going to check if that neighbor has been already discovered or not. Now what tells us whether the neighbor has been discovered or not? Well, in BFS it was really the visited array which told us that, and so far we don't have any visited array here, so let's pretend that we are going to add that in here. So apart from captured, let's say we also have another array called visited, which is also a one-dimensional array of size n initialized to -1, and the visited value of the source, which is the vertex of ID 0, is also 1. So every time a node is newly discovered, that is the point where we mark it as visited. So we say if the neighbor has not yet been visited, so if the neighbor is not visited, that means visited of neighbor is equal to -1. What are we going to do? We are going to mark it as visited. So we'll say visited of neighbor is equal to 1, and then we will add that neighbor to the priority queue. So I'm going to say priority queue dot append, or let's say insert, priority queue dot insert neighbor, and we also have to specify with what priority. So the priority value is going to be equal to the cost of the edge. So that's what we do if the neighbor hasn't been visited yet. Now what if the neighbor has been visited? If the neighbor has been visited, we are in this else clause. So let me write down in comments here that the neighbor is visited. We might still have to look at the neighbor, because if the neighbor is visited, it could be lying either on the left hand side, or it could be lying in the priority queue on the right hand side, right? This is where the neighbor could be, or this is where the neighbor could be. If it lies on the left hand side, we don't care about the edge to that neighbor, because our growing structure already has subsumed it, right? So we will worry about the neighbor only if it has not yet been captured. So if the captured value of the neighbor is still -1, it has not yet been captured, that means we are looking at this kind of edge which is going to the neighbor. We are going to look at the cost of this edge, right? So if the cost value happens to be less than the current priority value of the neighbor. Now how are we supposed to know what the current priority value of a neighbor is? Does a min heap provide us that information? Well, no, it doesn't provide us that information. There's no way for us to search for a vertex in a min heap with a specific priority value. So if we want to maintain that information for each vertex, we have to again go back and add an additional array for each vertex, which is going to store that priority value. So I'm going to assume here that we do that. We go back to our initialization, and let's say we add an array called importance, okay, an importance array, which, like the captured and the visited array, has been initialized to -1s, and every time we add a vertex to the priority queue, we are going to set its importance. So when we inserted a neighbor into the priority queue, this is where we go and say that the importance of that neighbor, or the priority value of that neighbor, is equal to the cost. And so at this point we are going to say that we are looking across this edge from the node to the neighbor, and we want to see if this edge has a lower cost, a lower weight than the current priority value of that neighbor. So if the cost happens to be less than the current priority value of that neighbor, right, importance of that neighbor, then we want to update the priority value of that neighbor. We want to basically set the importance value of that neighbor to be this lower cost number, which also means that we might have to move that neighbor around in the priority queue to bring it further to the head of the queue, closer to the head of the queue. So this is where we appeal to that decrease key operation. We have to do a decrease key operation on the priority queue. We have to say go to the neighbor, go to this vertex called neighbor in the priority queue, and set its new priority value to be equal to the cost. So I'll get to how this is this could be implemented in a heap in a minute. Let me just complete the structure of this code. So if we find that the cost is lower than the existing priority value of the neighbor, that means this is actually the least cost cut edge going to that neighbor. So we update the priority value of that neighbor. And now at this point we will go back. We are done with this loop, so we will go back and again pop the next node out of the priority queue. We will set it to, we'll mark it as captured. We will look at its adjacency list. Its neighbor can be of three types again. Either it's not been discovered, it's being discovered for the first time, in which case we mark it as discovered and we add it to the priority queue with this particular priority value, and we mark its importance also in the array. Otherwise, if the neighbor has been visited, there are two options. Either it has already been captured, in which case we do nothing, or it still lies in the priority queue on the right hand side. So if it still lies there, its captured value is going to be -1, even though it has been visited. The fact that it's not been captured means that it's in the priority queue, and we will check if the edge to it has a lower cost than its current priority value, and if so, we will update its current priority value. So at the end here, we will come here once all the vertices have been popped out of the priority queue. So assuming that the graph was originally connected, we will eventually be able to visit every vertex in the graph. It will be added to the priority queue at some point, it will be removed from the priority queue at some point, and every time a vertex is captured, we are updating this total cost. We are adding one more edge to our growing structure, and so the total cost here is going to be the cost of the minimum spanning tree. And so if we return total cost here, that's going to exactly correspond to the lowest cost, the cost of the minimum spanning tree. Now in order to quantify the time complexity of this code, we need to understand how this decrease key operation would be implemented on a min heap. So let's say that this is what our min heap looks like. We have a bunch of vertices lying inside this priority queue, and they are each associated with a priority value, an integer priority value. And let's say that at some point during the execution of Prim's algorithm, we find an edge going across to the right partition, which goes to V8, and the current priority value of V8, as you can see, is 7. But let's say this edge had a weight of 1. So this means that the priority value of V8 needs to be updated to become 1. Now in order to change the priority value to 1, we have to get to the location of V8 in the min heap. If we can't get to it, we can't change its priority value. And so the question is, how do we get to V8 in the heap? Now this is an added complication when we are implementing our own heap for the purpose of executing Prim's algorithm, because we also now need to have these direct references. Given a vertex ID, I should be able to directly access the location of that vertex in the heap in order to decrease its priority value. So I have to go to index 8, locate a pointer to the current location of this vertex in the heap, and that's how I will be able to reach V8, because a heap doesn't allow me to search for V8. How do I get instant access to its current location in the heap? I need this auxiliary structure, kind of like a hash table or an array with pointers to the current location of each vertex in the priority queue. So following this pointer, I reach V8 and I change its priority value to a 1. So I'm going to erase this 7 and I'm going to make it a 1. And when I make it a 1, what will happen is that the heap property is now violated. If you look at the priority value of its parent, it's 5. 5 is more than 1, and so the heap property is violated. If this node happened to have children, the relationship with its children would still be fine, because by decreasing the priority value of this node will still remain smaller than the priority value of its of any children that it might have. So we don't look below, but we look above to see if the heap property is violated, and indeed it is in this case. And so we do the same thing that we did when we ran into this situation while inserting an item into the heap, which is we are going to try to swap these two and try to bubble up this vertex v8. So let me do that. I'm going to erase v8 comma 1 from here and v4 comma 5 from here, and I'm going to write v8 comma 1 here and v4 comma 5 here. So we have swapped the two nodes, and now v8 comma 1 has risen to this location. Now we again compare it with its parent. We see that the priority value of its parent, which is 2, is still more than 1, and so we have to repeat this process. We have to again erase v8 comma 1 from here and put it there, and likewise v1 comma 2 is going to bubble down, v8 comma 1 bubbles up, and now v8 comma 1 has risen up to become the root, and now you can see that the heap property is maintained. The structural property of this heap was not violated at all, right? The complete binary tree shape was not violated when we changed the priority. It's the heap property that could get violated, and we can fix it by bubbling up the node with the lower priority value up until it reaches its correct level in the priority queue. So how much time will this take in the worst case? In the worst case, this could take time proportional to the height of this tree, and since the heap has a complete binary tree structure, the height of the tree is bounded from above by some constant multiple of log n, so the height is order log n. This means the maximum cost of a decrease key operation is going to be log n. So assuming that this is what would be required to implement Prim's algorithm using a proper priority queue implementation, what would be the complexity of Prim's algorithm? Let's go through that first, and then we'll come back to the question of what to do when we don't have these operations available in the libraries. So building the graph itself would have taken time that is proportional to order m plus n. This would have taken time order m plus n. Initialization and looking at the neighbors of the source vertex, inserting the neighbors into the priority queue would have not taken more time than order m plus n. We will account for these insertion operations into the priority queue, the decrease key operations and the extraction operations separately in just a moment. But looking down over here, we see that we have this while loop which is going to run, and in each step we are extracting the next node from the priority queue. That extraction operation is going to take log of n, where n is the size of the priority queue. Each time we extract a node, we are looking at its adjacency list and potentially updating the priority of the neighbor in the priority queue. So the code looks a little complicated, but conceptually what's happening is that each vertex at some point is going to be discovered, at which point it is going to get added to the priority queue. So I'm going to show the I'm going to account for what's happening to each vertex separately. So each vertex is inserted into the priority queue at some point, and that could take time order log n, where n is the maximum size of the priority queue, right? The maximum size of the priority queue is going to be n, because at the most the priority queue can hold most of the vertices in the graph, so it can't grow to size more than n. So we'll say the worst case time for an insert is order log n. Now at some point we might have edges coming into this vertex from the partition on the left side with priority values that are smaller than the current priority value of that vertex. So in which case we might have to do a bunch of decrease key operations on the vertex, which could take order log n time, each of which could take order log n time. Let me just mark the fact that there could be multiple such operations, and finally the vertex is going to get extracted out of the priority queue, and that extraction operation is also going to take time, order log n. So how do we quantify the total amount of work here? Well, what we'll do is we will treat the insertions and deletions together. Since we don't know how many times we'll be doing the decrease queue operations, let's account for the insertions and deletions first. Each vertex is inserted and deleted from the priority queue once, and so combined across all vertices, this total amount of work done is going to be order n log n, right? Log n times n. Now, how many times is a decrease key operation going to happen on a vertex? Rather than look at how many times it's going to happen on a single vertex, let's see how many times the decrease key operation is going to happen across the execution of the whole algorithm. Because we know that a decrease key operation is happening when we are looking at the adjacency list of an extracted node from the priority queue. So in the worst case, every time every edge out of that node might cause a reevaluation of the priority value of the neighbor on the other side, right, assuming that neighbor lies in the priority queue. So let's say that the maximum number of decrease queue operations that could happen would be m, right? Since there are m edges in the graph, each time we look across an edge, maybe that's going to result in a decrease key operation on the vertex on the other side. So even if that happened, the total cost of the decrease key operations would then be order of m times log n. So the insertions and deletions together take order n log n, the decrease key operations on the whole take order m log n, and so the total complexity of running this code would be the cost of initialization, which was just linear in the size of the graph. The dominant cost is going to be these priority queue operations, order n log n for inserts and deletes, and order m log n for the decrease key operations combined. So assuming that the graph is sparse, that means the number of edges is proportional to the number of vertices, that means m is order n. The combined cost, or the total cost, the total time complexity, would be order of m log n plus n log n, and if m is basically order n, assuming the graph is sparse, this is going to be order n log n. So you can see that the code looks fairly complex, but asymptotically it's the same. This is the same as the complexity we had for Kruskal's algorithm, which used a much simpler union find code. So when you're given a minimum spanning tree problem in an interview, you don't even have to think about it. Just go for Kruskal's algorithm. Don't try implementing Prim's algorithm, because you can see already that the code is fairly complex. Of course, the actual code you'll write in an interview is not going to be this, because I already told you that the decrease key operation does not exist. We still need to look at the actual code you'll write, but you can already get a sense that it's going to be more complicated than Kruskal's algorithm. But nevertheless, this is the time complexity we would have, assuming that the decrease key operation was available in the way that we discussed.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today